In this video, we're going to look at basics for hypothesis testing. And then that's going to lead us into a later video where we're going to talk about hypothesis testing for proportions and means. So let's get started. Let's talk about some of the basics. When we talk about hypothesis testing, we are testing the claim that something is going to happen. Either we want the mean to be less than a value, or we want to test a proportion that's equal to, but we're looking for those keywords. Test the claim that. So we're going to have two hypotheses. We're going to have a null and we're going to have an alternative. Now, I'm used to this notation H1. Some textbooks will use an HA or H lowercase a. I think our textbooks does that. I'm just really used to using this H1 notation, so that's what I'm going to use. The null hypothesis is H naught, and it's pronounced H naught. It's going to have that little zero there. This is always going to be an equal to statement, and then your other one is going to be one of three things. It's either going to be not equal to, less than, or greater than. And that type of symbol there will tell you what kind of test you have. If you have a two-tailed test, you're going to see the not equal to. If you have a less than, then that means you're going to have a left-tailed test. And if you have a greater than in that alternative, then you're going to have a right-tailed test. So that level of confidence is going to be split between the two tails. Our alpha value will be split between the two tails if we have a two-tailed test, so a not equal to sign. We have a left-tailed test, then all of it is going to be in the left tail. Now, that's really different from when we did confidence intervals. With confidence intervals, we always split it equally between the tails. And then a right-tailed test, if we have a greater than sign in the alternative, then we know it's going to be right-tailed. So let's talk about how do we identify the null and the alternative hypothesis. We're looking for keywords. So let's look at some examples. The mean annual income of employees who took a statistics course is greater than 60%. Okay, so it's giving us a lot of information here. We're talking about the claim about a mean, and it's greater than 60%. So for that first one, we could come up with both hypotheses based on that information. We're looking at a claim about the mean. So I'm using my mean symbol there. And it tells me it's greater than 60,000. I think I said percent earlier. Sorry about that. I was looking at the next one. So the null hypothesis, H naught, is always going to be an equal to. So we always use the same symbol for both. We always use the same value for both. It's just now we've got an equal to for the null hypothesis, greater than, because we have that keyword greater than for the alternative. Number two, the proportion of people aged 18 to 25 who currently have COVID-19 is equal to 20%. So keywords here, proportion, and is equal to 20%. In this case, we are testing the claim about a proportion. I'm going to use P here for proportion. And they actually gave us the null hypothesis at 20%, and we're always going to write that as a decimal. So the alternative would be not equal to 20%. Take a minute, pause the video, see if you can come up with the hypotheses for 3 and 4. Then come back and check your answer. So 3, the majority of college students have credit cards. Majority implies a couple of things. It implies that we are dealing with a proportion. And majority would be greater than half. So they're giving us that null hypothesis here. I mean, the alternative hypothesis. The null is going to be equal to half. And then 4, the mean age of college students is less than 25. mean age. We're testing the claim about a mean there. So I'm using my mean symbol. Less than 25 is the alternative. Equal to 25 would be the null. Okay, now let's talk about, is it left, right, or two-tailed? This guy has a greater than in number 1. So this is a right-tailed test, which means that all of our alpha value would go in that right tail. This one is a not equal to, so this is a two-tailed test, which means that our alpha will be split between the two tails. This one is greater than, so it's right-tailed. So our alpha value is going to go in that right tail. And this one is less than, which means we have a left tail test. So alpha would go on the left tail. So we're building all these different skills, and our goal is to be able to put it together in the next video, or in another video, to conduct a full hypothesis test. So can we identify null and alternative hypothesis? We are good. The next thing we need to talk about is the test statistic. And we're talking about test statistics here just for testing one proportion or one mean. There are other ones if we want to test two, but I just want to give you an idea of what they're going to look like. The test statistic is a value used in making a decision about the null hypothesis. It's found by converting the sample statistic to a score with the assumptions that the null is true. So if we're looking at a Z, we're testing the statistic for a proportion. Test the claim that the majority of people own credit cards. That would be the example of a proportion. We're going to have p hat minus p over the square root of p times 1 minus p over n. N is how many items are in your sample. P is what we're testing. P hat is the sample proportion. T, we're testing the claim about a population mean with the standard deviation unknown. So it's x bar minus the mean, that's what we're testing, over the sample standard deviation divided by the square root of n. So left tail versus right tail versus two tail. Two-tailed test is going to give us critical region and the two tails of the curve. So that's what I was drawing that picture of earlier. We're going to take that value and we're going to split it evenly between the two. If we have a left-tailed test, then all of it gets put in the left tail. If we have a right-tailed test, then all of it gets put in the right tail. The p-value is the probability of getting a value of the test statistic that is at least as extreme as one representing the sample data, assuming H not true. So, in other words, your p-value is really your probability of being beyond that test statistic. And we'll talk about and show pictures about what that looks like in a minute. We're just building vocabulary right now. So what are some more definitions that we need? We need the critical region. The critical region is your rejection zone or your rejection region. The set of all values of the test statistic that causes us to reject the null. That's where your alpha is going to come in. It's going to have that alpha value in that left tail or that right tail or in both tails. If it's a right tail test, your alpha value is here. We can find that critical value which separates the critical region from the rest of the graph. Alpha is your significance level. And that critical value, like I said, is going to be tied to your alpha value. So how do we go about finding critical values? Well, we're going to talk about Z ones in this. And then when we start talking about hypothesis test for the mean, then we'll do some T's. But let's just kind of get our feet wet. We want to find some critical values. So it's giving us some information. The first one is that we have a two-tail test and alpha is 0.05. Sorry, 0.01. Okay, that is the area in both tails, which means I've got to split that in half because I got to have an equal amount in each tail. My critical values would be this cutoff score that separates those critical regions. So we're going to go to SALT, distribution calculators, normal distribution, mean 0, standard deviation 1, and we want that 0.005 in that right tail. And we're going to get that z-score value of 2.58. If we look at the left tail, we're going to get negative 2.58. They're going to be the same number. If it's a two-tail test, it's just one's going to be negative and one's going to be positive. And that's because of the symmetry we have with this graph about 0. And the fact that it's a standard normal. So our critical values are 2.58 and negative 2.58. Let's look at that second one. The second one's giving us some information. We have a right tail test, and alpha is 0.02. You're trying to find that cutoff score. So we're going to go to SALT, right tail test, alpha 0.02. And our critical value is going to be 2.05. So this is where you may want to pause the video, try the other 4, come back and check your answers. Number 3, left tail test. Alpha is 0.10, so that 0.10 has to be in that left tail. I'm looking for that critical value. Left tail, 0.10, negative 1.28. 4, they're telling us that the alternative is a not equal to, so this means a two-tailed test. So that alpha has to be split. So if I take alpha over 5 and split it, I'm going to have 0.025 in each tail. We're going to go to SALT, type in 0.025, and we're going to get negative 1.96 for the left one. That means the right one has to be positive 1.96. 5, they're telling us that the alternative is a greater than. Greater than means right-tailed. So all of that alpha of 0.05 has to fall in that right tail. So we're looking for that cutoff score. We're going to get negative 1.645. I'm sorry, just kidding, positive 1.645. Okay, I could switch this to right and you'd say that that would be a positive. This is the only one that I've ever seen this rounded to 3 decimal places because 0.05 is a common area to have in that tail. So just 3 decimal places makes that one a little more accurate. And then that last one is less than. So that means left tail. So I have 0.05 in that left tail. And I'm going to get a negative 1.645 for that critical value. So that's how we find critical values. So when we conduct a hypothesis test, what do? You've got 2 options for this. You can use the p-value method, where you're comparing p-value and alpha. P-value is the probability of being beyond the test statistic. The test statistic is something that we're going to have to compute. That's where these formulas come in. That critical value is tied to the critical region, which is tied to alpha. So if your p-value is less than alpha, then you reject the null. If p-value is greater than alpha, then you're going to fail to reject the null. Right, this is my favorite way of doing it. So I will show you both methods, but that's the one that I tend to use. Traditional method, says that if the test statistic falls in that critical region, then you're going to reject H naught. It's really the same thing as this. That p-value being less than alpha is pushing that test statistic in that critical region. If the test statistic does not fall in the critical region, so if the test statistic were to fall over here or here, then we would fail to reject the null hypothesis. Now notice everything is based around whether we reject or fail to reject the null. So we're not really proving the null, we're only determining if there's enough evidence whether we're going to reject the null. So we really want to write that conclusion in terms of the alternative hypothesis. And you can kind of compare it to the legal system. When someone goes up for trial for some kind of crime, they're either guilty or not guilty. We don't say that they're innocent. We just say there's enough evidence to convict or enough evidence where we don't have enough evidence to convict. So it's really similar. So let's look at finding p-values next. We're going to use a 0.05 significance level in all of these. And then we're going to determine what we're going to do about the null hypothesis, whether we're going to reject or fail to reject. So let's look at that first one. The test statistic is a left tail test and is negative 1.25. So let's draw a picture of what's going on. Left tail test. Here's my negative 1.25. I'm going to find that area. So I'm going to find the probability that z is less than negative 1.25. That's my p-value. So I'm going to solve. Probability that we are less than negative 1.25. My probability is 0.1056. Negative, sorry, 0.1057. So I know that this area here is 0.1057. That's my p-value. Notice that p is bigger than alpha. If p is bigger than alpha, then we are going to fail to reject. So let's look at that next one. Number 2, test statistics in a right-tailed test. So my test statistic is 2.50. P-value would be whatever this guy is. So I need to find the probability that z is greater than 2.5. Go to salt. Probability z is greater than 2.5. And I get 0.006. That's my p-value. In this case, my p is less than alpha, so we are going to reject. Let's look at the third one. And this is where you may want to pause the video, try it, and then come back and check your answer. So in 3, we are looking at a two-tailed test. And that test statistic is 1.75. And that means that one in the left tail is negative 1.75. So we need the probability that's in both of those tails. We have to be careful there. So in the right tail, 1.75, we get 0.0401. That means this is 0.0401. So my p-value is going to be this plus this, which is 0.0802. So my p-value, comparing it to alpha, is larger. 0.8 is bigger than the 0.05, which means we are going to fail to reject. Number 4. This is also a two-tailed test because of the not equal to. They're telling us that our test statistic is negative 2.75. So the other one is positive 2.75. Oops. I'm looking at that left tail. Negative 2.75. So I get 0.00, we'll call that 0.003. So if this is 0.003, then that means this one has to also be 0.003. So my p-value is the combined score, which is 0.006. P is less than alpha. So what are we going to do? We are going to reject. Number 5, because it says greater than, this is a right-tailed test with that test statistic being at 2.30. So I found that value in that right tail. Right tail, 2.30. I get 0.0107. P is less than alpha. We reject. And then 6. This is a left-tailed test. So that test statistic is in the left tail. Here's negative 2.95. Find that area. Left tail. Negative 2.95. I get 0.0016. 0.0016. P is less than alpha, then we are going to reject.